Okay, welcome back. Good afternoon. So this is our final week before the break, which I think is well warranted. Hey, so we had started talking about symbolic dynamics and coding and conjugacy and all these ideas, and today I'm going to spend more time on symbolic dynamics and shifts. Yeah, and then probably on Thursday we're going to start connecting this back into iterative function systems. But let me just remind you what we were discussing. We had this example. On the one hand, we had the doubling map on the interval, in other words, the sawtooth map. And we have this shift transformation as well. So the doubling map is acting on the interval, and the shift transformation, the specific one that I'm looking at, is acting on the space of all sequences with two symbols, 0 or 1. And how does it act? Well, you feed to it an infinite sequence of zeros and ones, and it just gets rid of the first entry and then shifts everything to the left. Right? This is sort of like a fast way of writing that. And we had this map, we defined this phi that goes from the interval to the shift space, which does this. You take your point in the interval, look at its binary expansion. So I guess this should be x0 over 2. So let me just put 1 over t here so that it makes sense. And then these numbers gives you a sequence, and the image of phi is that sequence for that specific point. And for this to sort of make sense, or rather for this to be a bijection, 1 to 1 and onto, we have to discard certain collisions. And one collision is when you have a tail in a sequence that has always zeros, because there's another way of writing it using repeating ones. We're saying, so for instance, you can just take the ones that has 1 repeating. And then this becomes a conjugacy. We discussed this last time, from the doubling map to the shift map, which means this, right? Phi composed with f equals sigma composed with phi, or we can write this, we can draw this commutative diagram. They're basically the same thing, which means that phi is sort of like a coordinate change. If I were to change my coordinates from whatever Euclidean coordinate I have on the interval to the shift space using this phi, the doubling map becomes nothing but the shift transformation. Another way of writing this is, of course, to write this, right? So you can take this to the other side. You can write it like this too. Okay, and another word for this particular conjugacy is coding. Whenever you have a dynamical system and you're conjugating it to some shift dynamics, that's called the coding. But there's more, which is that this phi is not just a bijection, but in fact it has certain topological properties. In particular, it's a topological conjugacy, and moreover, in fact, it's a bi-Hölder conjugacy. Now, what does bi-Hölder conjugacy means? Well, basically, I'm saying that phi is Hölder from here to there, and its inverse too is Hölder continuous. Relative to what, of course, which metric? Well, for the interval, we use we can just take the standard Euclidean metric. And for shift spaces, we had defined this metrics, this one parameter family of metrics back in week 1. So I'm just going to use that. And recall that for theta, a number that is larger than 1, and 2 sequences, so 2 points in the sequence space, their distance is this, which, if you were to write this out, you would get this. So this says, so I need to start with this, and then 1 over theta delta of omega 1, eta 1, and then 1 over theta squared, delta of omega 2, eta 2, and so on. And here, this delta of two things is the discrete metric, which means that, for instance, here, this value is 1 if these two symbols are different, and it is 0 otherwise. Okay? Any questions about these so far? Now, in the notes, I defined a bunch of other families of metrics that are very useful for shift spaces. I compared them, which ones are Hölder equivalent to which other one, which one is Lipschitz equivalent, and so on. But this is one very common sort of metric, and this is, I think, also the family that Barnes uses. Okay, so I'm not going to prove the whole thing. I'm going to go one way. I'm going to leave this direction to you. That is to say, I'm going to leave it to you to verify that phi that takes points on the interval and sends them to the sequence that is there, that is the expansion of the point, that is Hölder. But I'm going to do the other way around. This is somewhat technical, but still I think it is important to discuss this because this is an idea that people use all the time in dynamics. Oh, let me also verify, let me also give it as an exercise that relative to this metric, this space is compact. I can write this more generally. So shift space with M symbols relative to d theta metric is compact. Okay. Let me just abbreviate as psi the inverse of phi. Okay. Now I want something like this. I'm just going to write down the definition of what it means for psi to be Hölder. So I want to take two sequences, 2 points in the sequence space, apply both of them, the inverse map, which is psi. Now I have 2 points in the interval. Then I look at their distance. So what is the distance of 2 points on the interval? Well, it's just the absolute value of their difference. So I want to bound this by something like this. Let's say alpha. For some alpha, I want this. Right? That is what it means for psi to be Hölder continuous with Hölder exponent alpha. Okay, before going into this, let's first perhaps discuss sort of practical ways of thinking about two sequences, that is to say 2 points in the sequence space being close. So, how to think of 2 points in the sequence space being close relative to d theta. So let's try to understand what it means for omega and eta to be epsilon close to each other. Now, theta, this parameter, I fix it once and for all. You can fix it to be a specific number as well, but let's just leave it as is. It doesn't make it more simple. Well, 1 over theta is going to be a number less than 1, which means that if I were to keep taking powers of it, that's going to converge to 0. So that means that no matter what epsilon is, and I might as well assume that epsilon is less than 1, because I'm trying to understand what it means for 2 points to be close to each other. There's going to be some power, let's say k, such that 1 over theta to the k is going to be here. And then 1 over theta to the k plus 1 is going to be less than epsilon, or less than or equal to. So there is a unique k integer such that this happens. Any questions about this so far? I mean, this is sort of like, the Archimedean principle, if you want, but I'm applying it at a logarithmic scale, if you want. It doesn't matter. Something that decays, eventually I'm going to get some number that is less than epsilon. Okay, so let's say that these 2 points in sequence space is epsilon close. Which means that in particular they are this close. Okay, now let's write out this definition. Oops, sorry. So the first term is delta of omega 0 and eta 0. So this is the comparison of the first entries of the 2 points in the sequence space. And this number is 0 or 1, depending on whether or not they are the same or not. Well, certainly I'm assuming here, like I said, epsilon to be less than 1. If this were 1, that is to say, if the first entries were different, this distance would be certainly larger than this, which means that this has to be 0. In other words, their first entries have to be the same. Okay? And likewise for their second entries, or 0th. If this is 0th entry, then the first entries. This has to be 0 also. All the way up to this. After that, I don't know. And so plus dot dot dot, and then I go all the way up to here. So the kth term I'm looking at. And then of course the series continues this metric. K plus 1, eta, k plus 1. And it keeps going on like this. Again, this would have to be 0, because otherwise the distance would be not less than this number. Okay, this means that in order for 2 points in sequence space to be epsilon close, or in other words, in exponential scale, 1 over theta to the k close, that means that I need to have the first k entries of the sequences coinciding. Okay? So let me write it here. And eta must coincide. Any questions about this? So, if you watch a sci-fi film from the 90s that's about like hacking and stuff, how they're trying to come up with the ciphers and all that stuff. And typically it's like the first entry gets locked and then the second entry starts moving and then the third entry. That's sort of like, you can imagine that to be sort of a sequence of sequences converging to some sequence. Okay, that's sort of like the visualization you should have in mind. Okay, so that's that. So with this, now I can try coming up with this bound. Okay. By definition, this is 1 over 2, let me abbreviate it like this, omega n divided by 2 to the n, and starting from 0, minus the same thing with eta. Now, both of these, in analysis, you learn these kind of things. Both of those series converge absolutely, in which case you can sort of like do basic algebra with these things. So I can do this. And say that the distance between omega and eta is sandwiched between these two values. Let's do this. Doesn't matter that much. In this case, based on the same reasoning here, the first k terms of this should be 0. That is to say, I can write it like so. And starting from k plus 1, omega n minus eta n divided by 2 to the n. And then taking out this factor, I have 1 over 2 to the k, plus 1, I guess, 1 over 2, and then the sequence. So now it's a change of variables. N plus k plus 1 minus eta sub n plus k plus 1. I mean, the point is that this is a number that is bounded by something because this is only, so this numerator, each numerator is either 0 or 1. In any event, this is bounded by some geometric series so that this is bounded. And in fact, it's bounded by 1 over 1 minus 1 over r, 1 over 2. So that gives you, what, 1 over, what does it give you? 2 over 2 minus 1 over 2 is 1 over 2, and then, so this is bounded by 2. With this factor, I get rid of this, so that I'm left with this. So we're almost there. The one problem here is that the bases are wrong, okay? So here it's 2, here it's theta. What you can do is you can choose theta to be 2, and then you would be done. Or you leave theta as is, and then you remember how to change bases for powers and stuff. So I want something like this. So this is sort of the general thing. A to the x equals b to the y. Now these bases really are, we're going to discuss this in a second, it's really, so the different number, theta or 2, they really depend, they are really the units of information. So depending on the field, people use different bases. So how to sort of solve this for y? I'll take the log of both sides. I have x log a equals y log b, so that y equals x times log a divided by log b. Yeah. Which of course is log a in base b too, if you want. But you know, here I can be ambiguous as to what log is relative to, but it should be relative to the same number, of course. In any event, applying this formula, now I have 2 to the k equals, or 2 to the k plus 1, equals theta to the k plus 1 to some power, which is log 2 divided by log theta. Now that is going to be my alpha. So that's sort of, you see the Hölder exponent is somehow the cost for changing the units when it comes to information. But then you see, this guy is bounded by this. So this is d sub theta omega eta to the alpha. Okay, so I was able to show this. Any questions? Well, here it seems like I'm assuming that omega and eta are close to each other to begin with. Well, while that is true, you can realize that any 2 points in sequence space has distance at most 1. So they are kind of close to begin with. So that's not an issue. Okay. About this information, let me just mention something about this. I guess I should put it over here. Oh, by the way, some of you have already started using this. So for instance, at this stage, we have that phi, or psi, I guess, is a continuous bijection from compact to some other space, which means that it's a homeomorphism. Okay, so it's already topological conjugacy by that theorem that some of you started using, but getting the Hölder continuity for the inverse requires some work. So, okay, regarding this information. Because a lot of these ideas are related to information theory as well. You know, notions like entropy or dimension, or some versions of dimension at the very least, a word about information theory, or some information theory. What you say is this: if you have a coin, let's say, that can be ordered, that is ordered heads or tails, or if you have a state that is ordered either 1 or 0, its information, so it has 2 to the, so if you have something that can be either 0 or 1, so it's an on and off switch, so it has 2 to the 1 states, and this exponent is how much information knowing which state this is gives you. So how do you get to 1? Well, you take log in base 2. And so you say that knowing the state of the system has 1 bit of information. So bit is 1 unit, a certain unit of information. Based on the same thing, if you do the same things with base 10, one Hartley of info, if you do it in base E, which is more natural perhaps from a pure math point of view, that's called a NAT. So whenever you see a log, if they don't sort of like mention what the base is, it's basically because of this. So from an information theoretical point of view, you're just changing the units. Instead of measuring inches, you're measuring centimeters, let's say, somehow. Okay, this is all I'm going to say for now, but it's still good to think about dimension, for instance, upper similarity dimension, as sort of like the information content of whatever fractal or attractor that you're looking at as well. Okay? Questions about any of this? Okay. Now, I want to give more examples of shifts and other things, but let me introduce some more terminology. Again, some of you started doing exercises about these things, but still. Basic definitions of dynamics. And I guess the most basic definition is for a subset of a set to be invariant under the dynamical system. I take an arbitrary set and a dynamical system on it. Again, you can define this more generally for more general dynamical systems, but let's just look at iterations. A subset A is F invariant if the preimage of A under F equals A. Recall that this doesn't mean that F is invertible. I'm not applying the inverse of F. So this is by definition some set, the left-hand side, which means it's the set of all those points that land on A in time 1. So this means, thus, if you're in A, and if you apply your dynamics once, you're going to land in A. But also, any point in A comes from some other point in A. And also, if A in A, and there is some other point B, let's call it, possibly different, such that F of B equals A. And there are certain exercises that some of you have been looking into as to whether or not these are important to have both of these statements. And really, this is sort of the most natural way to define invariance. Yes?
You said that wasn't the inverse of F, or?
It's not, yeah. So the left-hand side, we had defined this a while ago, that it's the preimage of a set.
Okay.
So all those x's in X such that f of x is in A. So pictorially, you have your big space X, and you have your A. Well, if you start with any point here, it's an initial condition, let's say, and apply F to it, you're going to land to some other point, not necessarily to the same point, it doesn't need to be a fixed point, but certainly you're going to land at some other point that is in A. And furthermore, if you started at A, in fact, there is possibly some other point in A that is the past. So that point that you started with, in fact, was already in A in the previous time step also. Yes?
So if it doesn't need to be invertible, does that mean you can have like multiple B's that both equal?
Could be, yes. Could be, yes. 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 Yeah. Many questions about this? Now, we can define what it means for something to be a subshift instead of just shift. Any closed shift invariant subset of the sequence space is called a subshift. Oh. We can do this with bi-infinite sequences as well, but this is sort of the model that we're going to use more often. Be the shift on M symbols well, perhaps let's try it like this. For any shift invariant like this. For any shift invariant closed subset, the restriction of the shift to that closed subset is called a subshift, which I'm going to denote by sigma sub A. So that means that not only am I asking A to be closed from the perspective of metric spaces, so if I were to take a sequence of points that converges to something, I want that limit to be in A, but also I want the set to be shift invariant also. Okay. In a second, I'm going to give examples. In fact, perhaps I should give an example. For instance, this Hadamard example is a subshift. So recall that for Hadamard, let's use instead of ABC 0, 1, 2. So we have the full shift, which is the shift acting on 3 symbols. And then let me define A to be the set of all those omegas such that no two consecutive terms of omega is the same. So, let's try it like this. Recall that the Hadamard example was the case when we were looking at 3 circular obstacles, and we were looking at all the trajectories, Billiard trajectories, That sort of you can get by bouncing the billiard on these. And of course, if you hit one of these, so if at one stage you hit 0, you can't hit 0 the next stage. You have to hit either 1 or 2. So that's sort of one way of coding this. So that this becomes sigma sub A. Let me leave it as an exercise to show that this is indeed a closed subset, closed invariant subset. Closed and shift invariant. Okay. Now here's an important idea. How do you define closed subsets? Well, you take your alphabet. In this case, I have M symbols. And using that alphabet, you construct what are called words. And words are finite strings. And then you take a set of words that you call are taboo words. So that's going to be an exercise as well. Let tau or T be a set of finite strings of words in the alphabet A, which is 0, 1, all the way up to m minus 1. So this tau or T is going to be the set of taboo words. Then A sub T, which is the set of all those sequences that contain none of the taboo words, is a closed subset. Any, let's say, T in curly T. So you take a bunch of words, you call them verboten, and you look at those sequences that doesn't contain them. So they're, valid words, they're valid sequences. Put them to a set, put them into a set, and that gives a closed shift invariant subset. And in fact, that's the first part. The second part is that any closed shift invariant subset can be written like this. Is of the form A sub T. So what is the set of taboo words in the case of Hadamard? Well, it's these. Okay? Any questions about this so far? Okay. Now, a subshift, a restriction like this, is called a subshift of finite type if you can define it by forbidding finitely many words. So for instance, the Hadamard shift is a subshift of finite type. You can just take these three words, forbid them, and then that defines the set. Of course, the problem here is that in your taboo words, you can put 0, 0, 0 as well, but sort of that's redundant because you're already prohibiting 2 zeros consecutively. So you don't need to forbid 3 zeros consecutively in addition to that, okay? So let's call it sigma sub A is of finite type if it can be defined by a finite set of taboos. Taboo words. Okay, so one example, like I said, is the Hadamard example. Here's another example that is really sort of connecting this theory of shifts and subshifts to Markov chains. Yes?
Do you remember what the definition of a taboo is?
You just define, you take it as a taboo. There's no intrinsic definition.
Yeah, gotcha.
Yeah. So in the Hadamard example, I chose the set of, so M was 3, and I chose as my taboo words 0, 0, 1, 1, and 2, 2. I said those are verboten, and then I looked at the set of all those sequences that doesn't contain them. So here's another example. I'm going to draw a graph. Let's look at this. Okay, I have 3 states, 0, 1, and 2. And by this, when I draw this graph, I'm really thinking about the sequences that can be written by following this graph. So for instance, the sequence that is constantly 0 is in the set, because I can start at state 0 and keep, using this arrow, keep using this symbol. But also, I can do something like this, for instance. I can go from 0 to 1, and then 0 to 1, 0 to 1, and so on. Or I can do perhaps 0, 1, 0, 0, 1, 0, 0, 0, 1, and so on. 0, 1, 0, 0, 1, 0, 0, 0, 1. Or perhaps something like this. I can start at 0, or maybe let's start at 1. 1, 0, 0, 1, 2, and then 0, and so on. 1, 0, 0, 1, 1, 0, 0, 1, 2, 0, 0, 1, 2, 0, 1, 2, 0, 1, 2, and then maybe the rest is all zeros. The point here is that once you sort of like decide to abide by this graph, that means that if you, at some stage, see a 1, you cannot see another 1 right after it. You have to switch the states. Or if you see a 2, it says that to the left of it, you have to see a 1, and to the right of it, you have to see a 0, and so on. How many of you have seen something like this before, at least the graph? I mean, if you took linear algebra from me, you saw these kind of things. So this is also one of the reasons why you call subshifts of finite type that can be written of this form a topological Markov shift. Or a Markov chain. The point here is that this word Markov, it's a Russian mathematician, but in specific, it signifies that this system doesn't have any memory. So if you're at state 2, for instance, you don't look back at your past to figure out what you're going to do next. What you're going to do at the next stage is completely determined where you are today. Okay, no memory. So any topological Markov chain is an SFT of a specific type. Let me add one more thing here. One of the reasons why people look into these topological Markov chains, that is to say subshifts of finite type that can be defined like these diagrams or graphs, is that you can apply linear algebra to them. Because to each graph like this, you can associate a matrix. And that's called the adjacency matrix. There are many other matrices you can associate to a graph like that, but that's sort of like the starting point. And for us, I mean, at this stage, at the very least, a matrix is nothing but an array of numbers. So I'm going to associate to this graph a rectangular or square array of numbers. Let me just leave it as is. So it's going to be 3 by 3, 0th state, first and second state, 0th, first and second. And this adjacency matrix is going to be a 0 or 1 matrix. That is to say, any entry of it is going to be either a 0 or a 1. And how do you populate this matrix? Well, you say, where can I go from state 0? I can go to 0 or 1. And so you put 1 here, because from 0 you can go to 0. 1 here, because from 0 you can go to 1. But here you put a 0 because you cannot go from 0 to 2. Okay, based on this graph. From 1, you can go to 0, and 2, you cannot go to itself. From 2, you can only go to 0. Okay. The point here is that this array of numbers now compressed all the information there is about this into one matrix. And of course, you can, if you have a square matrix, you can iterate it and so on, and figure out certain properties of it. You can look at eigenvalues of it. You can look at eigenvectors of it, blah, blah, blah. And those properties say something about the topological Markov chain, or in other words, the shift dynamics that is sort of defining, that is associated to this. And of course, if you looked at things like PageRank, that sort of, this whole idea of the PageRank is, again, based on these ideas. So it's a very useful way of modeling things. Questions? Okay, let's take a 5-minute break, and then when we come back, we're going to look at more examples. Are we all back? Okay, let's continue. Welcome back. So here's a very nice exercise. Looking at this topological Markov chain, or the SFT for it, I just claimed that this is an SFT, but you need to, in order for a shift to be an SFT, or a subshift of finite type, it has to have finitely many taboo words. That is to say that you should be able to define it by forbidding only finitely many words. And so it's a very nice exercise to find the set of one set of finite one finite set of taboo words for this shift. Here's another example that's going to be important. But before going into this, I'm going to discuss this example, which is called the even shift. Now I have two symbols. So I'm looking at the set of all those sequences that can be written a 0 or a 1 at any entry. And the rule that defines the shift is this. Between any two 1s, I want an even number of zeros. Now this is still, it's a closed, so it's a subshift. That is to say, it is a shift invariant and it's closed, but this is not of finite type, right? Because, so perhaps I should write it here. Between any two 1s, I need an even number of zeros. So this word is verboten because it has 1 0. And so is this. And so is this. And so on. I hope you all agree that there's no way for me to summarize this whole thing by saying, by forbidding finite many words. There's always more words I should forbid. So this is a subshift, but not a subshift of finite type. But not of finite type. It turns out that this is still sort of not as general as you can go. It's not a finite type shift, but it's the next best thing, which is called a sofic shift. But let's not get into that. It's something that people look into as well. But yeah, so no, sofic. It's a Hebrew word, as I understand. Yeah. Okay. So now let's look at this. This is a finite type example. I'm looking at sequences that can be written using 0 and 1 and 2. And I'm forbidding the word that is 1. That is to say, I'm looking at all those sequences that contains no 1s. Omega in shift such that no NP of it is 1. So it can have 0, 0, 0, 0, 0, or 2, 2, 2, 2, 2, or 0, 2, 0, 2, 0, 2, and so on. All those words, all those sequences, rather. But not any sequence that contains at least 1, 1 somewhere. Is this set somehow familiar to any of you? It should be, because some of you discussed this in previous reports, actually. Perhaps without using this terminology, but it turns out that this is yet another way of describing the standard Cantor set. So, continuing from here. Is equivalent, let's say, is, what word should I use? Okay, I'm going to be safe. I'm going to say homeomorphic. To the standard Cantor set, which, as we know by now, is a subset of the interval from 0 to 1 that you obtain by getting rid of the middle thirds, as they say. So this is step 1, and then in the next step, you get rid of this piece. Okay? And then in the next step, you get rid of this piece and this piece, and so on. Now, in this case, I'm sort of subdividing the interval, you might imagine, into 3 equal pieces. So instead of looking at binary expansions this time, you might as well look at triary expansions. That is to say, you can take a point in the interval and write it using powers of 3 or 1 over 3. So x0 plus, maybe I should write it like this. 1 over 3 times x0 plus x1 divided by 3 plus x2 divided by 3 squared, and so on. At the end of the first step, so maybe I should say this. This is the first first sum n in the series that defines x. And in this notation, I'm imagining xi, each of these terms, to be 0, 1, or 2. But when I'm defining the Cantor set, going from step 0 to step 1, I'm actually forbidding x0 to be 1, because this corresponds to 0, this corresponds to 1, this corresponds to 2. I'm saying, by getting rid of this piece, that x0 cannot be 1. Any questions about this? Now, from going here to there, I'm saying not only can x0 not be 1, but also x1 too cannot be 1. And so on. You keep iterating this idea and show this. You get this, which is exactly that shift that we got over there. Okay? Yes?
Could this also be described as just 0 and 1 without the
Yes.
2? Okay.
Yes. That's another way of coding it. You have multiple ways of coding things. Yeah. Yes?
The homeomorphism is bothering me because earlier we looked at how 2 addresses in here correspond to the same real number. So how can the map be bijected if 2 different elements?
Well, again, I'm sort of getting rid of one of those schemas, let's say. Let's say that I'm forbidding in this expression 0 tails or something like that. No, in this case, actually, you don't need to do this because yeah, let's think about this. So for instance, 1 in base 3 is 0.22222, or 1.0000. But I'm taking everything to be at most, not more than 1, which means that 1.0000 is really coding something that is beyond this. Yeah. Or if you were to look at this point, for instance, one way of writing this would be 1111111, or you can look at it as 2000000. But I've gotten rid of the 1111 anyway. Yeah, I mean, it's like when you're first learning these things, it's like you get paranoid about these kind of things. And in more complicated contexts as well, this problem of 1 point in the attractor or whatever coming from having 2 different expressions does become a problem. Any other questions about this? Okay. Okay, so let's think about this then. So what is this homeomorphism? It's again this expansion. So here, what I said was, if C is this Cantor set that I get at the end, And just like we did for the doubling map, if I were to take C, a point in C, expand it using base 3, and then map it to the sequence that corresponds to it, I said I get a homeomorphism. And again, let me just stipulate that this is a Bi-Hölder homeomorphism, in fact. But let's think about this now. Because this, the target, it's a certain subset of shift space. That's fine. It's closed and compact and all that. That's all good. But furthermore, it has a dynamics on it, which is a shift. But on the Cantor set, we don't really have necessarily a dynamics. But somehow there should be a dynamics here. What do you think? So any guesses as to what the dynamics on the Cantor set should be? Maybe I should be more explicit about this. Okay. This is a standard Cantor set. It's a subset of the interval. And this is this subshift, which is a subset of the shift space. And it's a homeomorphism. Now, what is the shift here? What is the dynamics here? It's a shift. And you have this. I'm asking for the dynamics on the Cantor set. Almost. The problem with that is that the iterated function system that we use for defining the Cantor set, it has two functions. And the time parameter is not a subset of the integers like it is for the shift. So somehow this is related to what is called the chaos game. It's really the inverse of the chaos game, and it is deterministic. Okay, so we're trying to figure out this dynamics. Let's call it F. Now, formally, I can define F, right? Because phi is a bijection. And so I can say to go from here to there, it's the same thing as first applying phi, then sigma, and then phi inverse. Okay. That's fine, but it's somewhat abstract. So I want to understand what F does, how it operates. Now let's think about this. If in my shift space, I start with a point, I can sort of test out how it works. Let's say that I take an omega such that the first entry of omega is 0. Now, under this coding, can I say anything about where it should be on the interval? It should be here, right? Like, I don't know exactly where in this Cantor set, but certainly it cannot be on this part. It has to be somewhere here. Okay? So, going back, so Okay. Let's also look at the second entry or the first entry. Let's say that the first entry, let's say that it's also 0. That means that not only is it here, but it's also here. Okay, that is to say, in fact, that sequence is the expansion of some number that is between 0 and 1/9. Now I could have put here 2, and then this interval would have changed. Okay. So what happens if I were to apply shift to it? So now I'm going to chase the diagram. Okay. My omega here, I'm imagining, and I'm going this way, applying the shift. So let's read it like this. So I said 0, 0. Here, 1, 2, 3. Let's say that for whatever reason, I haven't uncovered these entries. Maybe I don't have enough resolution or whatever. But in any event, if I were to start here, apply my shift, now it goes to this. Right? Because shift operates by taking the first entry, it gets rid of the first entry, and then shifts everything to the left. So in a sense, I got rid of one decimal. Or in other words, if I didn't know the expansion starting from the second digit, after applying the shift dynamics, I actually don't know what's happening after the first digit. But of course, going from here to there, in terms of the points, really corresponds to this. So this is, how can I write this? So this is something like this, right? So it's here. This is here. So this is 1/3 x0 or omega 0, omega 1 divided by 3, omega 2 divided by 3, and so on. 3 squared. And this should go to something that says this. So omega 2 divided by 3 plus omega 3 divided by 3 squared, and so on. In other words, this dynamical system, which is the dynamical system that is conjugate to shift, is nothing but multiplication by 3. Which is like almost like what we did for the doubling map. There is one complication though, which is this, that if you had started with a point over here, it would have been multiplication by 3 and then something else. And so this is the whole description of f. Let me just write it here. Description. So f is going to be a dynamical system defined on the Cantor set. And it is a piecewise function. Okay. You can write this formally. Let's write it. F of x equals 3x if x is here. Otherwise, so I need some other formula. The point is that if this is alpha, I need to project it that way so that it becomes 3 alpha. So if alpha, let me just compute this, is 1 over x, then 3 alpha is this 1 minus 3 alpha, therefore is 1 minus this 1 minus this. To parse this expression, here's the sort of intuitive way of thinking about this. F does this, and with that I'm going to finish a class today. You take a point, that's your initial condition. Either it is closer to 0 or it is closer to 1. No matter to which endpoint it is closer to, you take that point and you expand the direction between x and that point that it is closest to by a factor of 3. So if x is here, you push it that way. If x is somewhere here, you push it that way. Okay. So if you look at Schroeder's book, there he's doing this for the Sierpinski fractal, and he calls this the Sierpinski game, or Sierpinski game. Okay. This is also the basis of this escape time algorithm that some of you have been looking into. Okay, we're going to discuss this more, but somehow, instead of looking at the iterated function system, which contracts everything, you look at things in backward time. So you expand things, because shifts are expanding transformations. They sort of make distances larger and larger. Okay, this is somewhat confusing, I'm aware, but look into specific examples, do calculations instead of trying to understand this in the abstract, and then it's going to hopefully start making sense. Okay, let's finish today and then continue on Thursday. Hello, good afternoon. So we have a couple things to discuss. So we've been talking about shift spaces, subshifts, and a bunch of other things. Today I'd like to connect that to the study of B-IFSs, iterated function systems in the sense of Barnsley. Probably we're not going to finish everything I wanted to say about this topic. So after the break, probably we're going to spend 1 or 2 classes perhaps discussing more sort of ideas. And then after that, we're going to start talking about dimension theory, which is really sort of the core of this class in a sense. A correction. Last time we were discussing this notion of invariance and forward, well, we didn't talk about forward invariance, but we talked about invariance and subshifts and stuff. I made a mistake, so I want to correct it. If I have a set and a function defined on it, f, so it's a dynamical system, and I take a subset, A is invariant if this happens. So the preimage of A under F equals A. This is a new definition now. A is forward invariant if the image of A under F is A. So, these look almost like the same. And if F is invertible, if it has an inverse, these two are the same, in fact. But because we're, for now, looking at non-invertible systems like shifts on one-sided shift spaces, they are not really the same. And in fact, last time when I was sort of talking about this condition, I in fact described this condition. I realize that as well. I'm going to mention that in a second. But the point here is that instead of defining a subshift as a closed shift invariant space subset, you want to define it as closed forward shift invariant. So the problem here is something like this. So first of all, I want the Hadamard example to be a subshift. Okay, I want that to be a subshift of finite type. Recall that Hadamard example was the following. You have 3 symbols. So let's say your alphabet is 0, 1, 2. And your taboo words is 0, 0, 1, 1, and 2, 2. So that no consecutive, so no 2 symbols have to, can be the same. Because that is supposed to model a billiard ball sort of bouncing. Then, of course, for instance, let me continue here. Let's look at omega. Let's say that it is 0, 0, and then 1, 2, 1, 2, 1, 2, 1, 2. Yep. Certainly, this is not in the subshift defined by this because it has a taboo word. So this guy is not in here, but if I were to apply shift to it once, well, I'm going to get rid of the first entry, then it's going to be 0, 1, 2, 1, 2, 1, 2, which is admissible. So this means that this Hadamard shift, A sub tilde, maybe I should use this, put a curly A here. This A sub t doesn't satisfy this property, but it does satisfy this property. So that's sort of like a minor point, but it's important. Any questions about this? With one of your colleagues in a previous report, we had some issues with the distinction between these. We had to spend some time. And you see, I was discussing all that stuff, and I made a mistake myself too. It's like it's, and you know, that goes to show you, I never think about, actually, when it comes to my research, I never think about one-sided systems. So for me, these two are the same. So I have to sort of like open up what it means. Yes?
So if something's invariant and invertible, does that imply forward invariant?
Yes.
Okay.
Yeah, yeah. So, yeah. Mm-hmm. Yeah. So I'm writing some, so in the lecture notes, probably you're going to see some exercises about the relationship between these two notions, and there's another one which is forward subinvariance and so on. Yeah.
So it doesn't need to be invertible, right?
No, no, no.
So do you remember like what the notation is then, with the f-1?
So this means as a pre-image. Okay, so perhaps I should draw this. I'm going to take a more general function from between two sets. So if I have a subset A, f of A is going to be the it's going to be f of x for x in A. So this is f of A. So somehow that's what happens. And if I have, maybe I should use a different color here. If I have a B in the target, then f inverse of B is the set of all those points here that are mapped to this. Okay, so maybe it's like this. So it's like the temporality is sort of backwards in a sense. Maybe let's open this up, actually, these two conditions. So here I'm talking about the equality of two sets. In order for two sets to be equal, one has to be inside the other one and vice versa. So okay, so let's start with this. This says that if A is an A, that A has to be in the pre-image, which means that f of A gets back to A. So this is the condition. This is sort of like a short way of writing this. This means that if X is an arbitrary point whose image under F happens to be in A, then X was in A to begin with. On the other hand, if I were to take this other condition, you're going to see it's almost the same, but these are like subtleties coming from set theory and stuff. So again, I'm going to open this up. F of A inside A and A inside F of A. Now this says that if A is in A, then F of A is in A. This is literally the same condition as this condition. So this statement is the same thing as this statement for any F and for any A. But this is different from this. This says that if A is in A, then there is some B in A such that f of B equals A. Silly games, but that's how math is done. Is this sort of answering your question? Yeah. Yeah, so last time when I said this, I was actually giving these two definitions. So I was describing these two. Instead, I should have described these two, which is in fact not the right condition for subshifts anyway. This is like a technical matter, but any other questions about this? Okay, let's get back to this example that we were discussing last time. Which is this. I took the alphabet 0, 1, 2, and as my taboo word, I said, okay, the only taboo word is the word of length 1 that is just 1. My alphabet is 0, 1, 2, and my set of taboo words just has 1. So that the subshift or finite type that is defined by this is the set of all those shifts, all those sequences with 3 symbols, such that you never see the symbol 1 anywhere. So it is either a 0 or a 2 at any time, at any spot. And then we were discussing this idea that this set is homeomorphic, in fact bi-Hölder homeomorphic, to the standard middle thirds Cantor set. And then we define this. A homeomorphism from C to the subshift that does this. Take a point x in C, so it's a number between 0 and 1, expand it using the triary expansions. Like this, and then take these entries in the powers on in the series and turn it into a sequence. So okay. So I left it as an exercise, I believe, that this is a biholder homeomorphism. Okay, what we were discussing was this. We don't really have sort of like a natural or obvious dynamical system on the Cantor set, but we have an obvious dynamical system on the shift space, which is shift. And so we have almost a commutative diagram, is what people would say. So if I had an F there, that would be a conjugacy. It would be a biholder conjugacy. Well, I'm not given that, but certainly from an abstract point of view, I can just define it as this composition. Can define F to be, so going from here to there, is phi sigma phi inverse. But you want to write it that way. So this is, and so perhaps we should discuss this as well. So this is a biholder homeomorphism. This too is a biholder homeomorphism. Shift is also continuous. So in fact, it's a continuous map, okay, from the Cantor set to itself. Now, one of your colleagues made the comment that this F is really the tripling map, if you want. In a sense, it is that statement is true, but in a certain sense, perhaps there's a better way of describing this function, so that we can relate it to B-IFSs. So now I'm trying to understand what F is. I want to have sort of like an explicit expression, closed form if you want. If I have a sequence, its zeroth entry is either a 0 or a 2 by the definition of this. So now I have a decision tree. If the zeroth entry is 0, then the point that corresponds to it under the conjugacy must be less than 1/3. So if I were to call x phi inverse of omega, it has to be not greater than 1/3. And likewise here too, if the zeroth entry is 2, that means that the point that corresponds to it under phi must be at least 2/3. So okay. I have here a sequence. If I were to apply phi to it, that corresponds to getting rid of the 0th entry. And now the new 0th entry is this guy. And then this is the new first entry and so on. This really corresponds to multiplying this by 3. So f of x is equal to 3x. Now, 3x is also 3x mod 1 because if x is less than 1 over 3, putting here mod 1 doesn't really do anything. It's the same function after all. Okay. Now, if x were here too, like your colleague remarked last time at the end of the class, if I were to apply the shift to it, again, it corresponds to multiplying by 3 mod 1, because now I have here a number which makes this point exceed 1. So I need to get rid of that. So in any event, this is 3x mod 1. Okay. Now the way I came up with these formulas last time was slightly different, but it's the same idea, which is this. Okay. Here I have 0. Here I have 1. Here is 1 over 3. Here is 2 over 3. And the description of f that I gave last time was this. Look at this x, which corresponds to omega under the conjugacy. If x is there, so that it's closer to 0, look at this distance. It's, of course, x, multiplied by 3. So in a sense, you're thinking of this point as a repeller, and you're sort of repelling this point by a factor of 3. So somewhere here, of course, it's going to land somewhere here. It's going to be f of x. If, on the other hand, x happens to be here, then look at this distance and multiply it by 3. Now, in this case, of course, f of x is going to be 3x, because this distance here is x, which means that this distance has to be 3x. In this case, though, the distance you should look at is 1 minus x, so that this distance is 3 times it. And so if I want to get the coordinate of f of x, I need to subtract this from 1 to get this distance. Yes?
So one thing I'm a little bit confused about is for defining x over here, which x equals 1/3 times x naught plus so on and so forth. This is an alphabet here, and I'm intrigued to know about how we're dividing it by 3. Because isn't it supposed to just be some abstract symbols? It doesn't necessarily have to be numbers.
No, no. This is in C. It's an honest to heaven's God. It's an honest to heaven's number.
Okay, gotcha.
Yeah.
We're just expressing it as like a sequence.
Yeah.
Like our series.
Yeah, I mean,
Okay.
you take a number, how many multiples of 1 over 3 are there in it?
Okay.
And then you have a remainder. How many multiples of 1 over 9 are there in
I
it?
see what I was missing here. That's
Yeah,
that's
yeah.
where
Yeah.
moving that into B here, generating the shift space from that.
Yeah. Okay, any other questions about this? So now, I'll leave it to you to verify that 3x mod 1 for x between 2 over 3 and 1 is equal to this number, this value. Okay, I'll leave that to you. So exercise. So 2 over 3 x1 means 3x mod 1 is this value. Okay. What I want to do is I want to still use these representations without this mod 1. So okay, so let's finalize this thought. So f equals g restricted to the Cantor set, where g is 3x mod 1. So it's a restriction of this tripling map. G is the map on the interval, which is defined by 3x mod 1. Okay. F is not exactly tripling map because the tripling map is defined on the unit interval or on the circle. It's defined on a nice set. But this F is defined on a fractal. That's sort of like the difference. But still, I want to get back to this expression and this expression. Okay. Now, this really connects it to B-IFSs. So let me just summarize this over here. So of course, I'm still imagining this to be inside the Cantor set, if you want. Then f of x equals 3x. And if x is between 2 over 3 and 1, and again, inside the Cantor set, then f of x is that thing. Let me consolidate some terms over here. So if I were to open this up, this is nothing but 3x minus 2. 3x minus 2. Let's try to invert these values. You're going to see why in a second. So if I were to say this is equal to y, then of course x equals y over 3. If I were to try to invert this guy, what is x? X equals y plus 2 over 3. Are these functions familiar? Okay. It's good. Because recall, so now I hope you're starting to see the connection between this, all this business, and B-IFSs. Because C is the attractor of the B-IFS, where the first function is this, and the second function is this. So if I were to put W1 of y, let's say, equals y over 3, and W2 of y equals y plus 2 over 3, acting on the reals, of course, but we can sort of take it to be a smaller subset as well. Then, and let's put them inside a set, so that this W is a B-IFS acting on reals, and C is the unique attractor for this. Furthermore, this is not only a B-IFS, but what we're going to call a totally disconnected B-IFS because of the following. So what does this mean? So what does it mean for C to be the attractor for this B-IFS? Well, it just means that C has this expression. Right, because the right-hand side is the Hutchinson operator and so on. C is a fixed point of the Hutchinson operator. This B-IFS, this particular one, is totally disconnected because not only this happens, but in fact, these two pieces are disjoint. They have no intersection, right? Because one of them is sort of shrinking things to the left and the other one is shrinking things to the right, which corresponds to this decision theory, of course. So this property, because of this property, we're going to call this W totally disconnected. Or disjoint is another phrase. And so, based on this, I can now write down F using W. I can say this. F of x equals the inverse of W1 if x is in this piece. And it is equal to W2 inverse if x is in the other piece. Okay. So this F, you see, is this dynamical system that we created by this conjugacy, but it's also intimately connected to the B-IFS. And this is called the intrinsic dynamical system on the attractor of W. So the intrinsic And by construction, this guy is Bi-Hilder conjugate to a shift system. Conjugacy to shift from F to shift. So it comes with this nicer dynamical system. Why is it nicer? Because it's all about taking sequences and shifting them one way. In a sense, it is rather simplistic compared to this description. Describing the shift is a lot easier. Any questions about this? Now, at this point, it would be very good to go to Barnsley's book, and he has a bunch of like fractals, and he's really sort of drawing trajectories of this guy, arrows and stuff like that. It would be very good to sort of like look at these pictures and meditate on them. Okay. I should mention that some of the addresses he's giving in the book I think are wrong, but be mindful of that. Okay, so now this is sort of the pattern basically that we want to handle. that we want to build for pretty much all iterated function systems. And this leads to this idea of addresses. I'm going to change the notation a little bit. So phi is going to go from a shift space to the attractor, but apart from that, everything is going to be pretty much the same. Now this, the Cantor example is very nice because of this property, this total disconnectedness property. We're going to see sort of where things start getting ugly a little bit. Okay, so let me fix some notation. Let's say I have n contractions acting on a complete metric space. So this is a B-IFS. Let me let L to be the max of the Lipschitz constants. It's going to be a number less than 1. Let me let A sub W the unique attractor of this B-IFS. Attractor. Okay. And let me also put sigma plus to be the space of one-sided sequences with symbols from 1 to n. So and of course there's a shift on it. Say there's a function phi, which is going to be sort of like the inverse of that phi, but never mind. There's a function phi from shift space to the attractor. I want that function to be nice, meaning I want it to be continuous, and I want it to be compatible with the iterative function system. We're going to discuss what that means in a second. Say there's a nice phi from shift to the attractor. Nice meaning it's compatible with metrics and stuff like that, and compatible with dynamics. So with topology, let me just say, or let me say metrics. And dynamics, or yeah, dynamics. I'm going to discuss what that means. It's going to take a while. At the very least, I want this to be onto. That is to say, given any point in the attractor, there is at least one sequence that this phi sends C's. Okay, so this means for any A in the attractor, there is an omega, at least one, such that this happens. In this case, for any A in the attractor, any sequence that is sent to A is going to be called an address for A. So the pre-image of A. At this point, I'm not saying that phi is invertible necessarily, but at the very least, it should be onto. So this is a set of all those sequences that phi sends to A. This set is called the set of addresses for A. For A. Okay. Any questions so far? Now things are going to get more like abstract, but as the moment you start feeling sort of lost, think back to the Cantor set example. Okay. Okay. So now I want to introduce a condition that seems somewhat perhaps natural, but turns out to be sort of like a technical condition that we're going to need later for this Moran-Hutchinson formula that relates the Hausdorff dimension, which we still haven't defined, but still, the Hausdorff dimension of this guy to the upper similarity dimension of the iterated function system. And that is the open set condition. So this is a definition. This B-IFS is set to satisfy the open set condition, satisfies and I'm going to give a condition that is not exactly the condition that Barnsley gives, but as far as I understand, there are 3 different or 4 different versions of this. If there is a non-empty open set of the big space X, such that 2 conditions hold. The first condition is that if I were to take U, apply each and every single one of my contractions to this U, take the union, that union has to be inside U. So this left-hand side is almost like the Hutchinson operator, except that the Hutchinson operator is not necessarily defined on open sets. We define it on compact sets. That's the first condition. Second condition is that the intersection of these any 2 images like this is empty. So if I is not the same thing as J, then the ith image is disjoint from the jth image. So in a sense, this is sort of like a separation condition. And there's an abbreviation for this, which is OSC. And let me also mention there are the variations about this definition. Sometimes people just look at open and bounded subsets. Sometimes, for instance, Barnsley looks at open subsets of the attractor and so on. There's a bunch of different versions. But this seems to be sort of, I don't know, this seems like easiest to state at the very least. Okay, so now we have, in fact, a trichotomy when it comes to B-IFSs, coming from this OSC condition. So first it bifurcates. Please keep this notation in mind. I'm not going to keep writing this. A B-IFS either satisfies the open set condition or it doesn't. Okay, that's the first separation. So maybe I should draw like this. So I'm looking at the same B-IFS. Either it doesn't satisfy or it does. If it doesn't, that's the worst possible situation. Okay, this is what Barnsley calls the overlapping case. In other words, you call the IFS overlapping. And you should think of this example. I have two contractions on the interval, and one of them contracts like this. This is the halfway point, and the other one contracts like this. Okay. Now, if I wanted to draw the graphs of these, we can do that as well. So, so the first guy is something like this. Okay, and then the second guy is something like this. Right, so here is the intersection. So there's like an overlap here, which corresponds to this piece. Okay. If it does satisfy the open set condition, then it bifurcates again. One is the best case, which is the Cantor set case, which is the disjoint case, or not. Totally disconnected. So the IFS is totally disconnected or disjoint. Or not. Then it's not totally disconnected, but it satisfies the OSC. Barnsley calls it just touching. This is the best case. This corresponds formally to this condition. Not only you have this open set where you have this empty intersections, but in fact, if you were to look at the images of the attractor itself, they don't intersect. Oh, sorry. Okay. You should think of this example. So the standard Cantor set. I'm just going to draw. Let me just draw one-sided. That's the first piece, and here is the second piece. Now, when I'm drawing this, I'm not really, I don't really need that this is like 1/3 and this is 2/3, and these two numbers can be different. The point is that these are separated. This piece is separated from this piece. In this case, this is sort of like the in-between point of the two, which is that this is the blue. And this one is the yellow. So there's an intersection, okay? Just touching case fails to have this condition, but the set on which it fails is small, in a sense. Yes.
Just making sure, for that middle one,
Yes.
the graph of it, whereas the first one's kind of like this, it would be like super split. Right?
Yes.
Where there's a lot
Yes.
of gap. Okay.
Yes. Yeah, you can sort of like imagine these two to be sort of like on sort of hinges, sort of like moves like this and like this.
Okay.
So it's like if they're like too much like this, it's in this case there's like a sort of like this critical condition where they're sort of like this.
And that's the just touch it.
Yes, and then if you go even further, it becomes this. Okay. Now in this case, the coding that we still haven't described, but we just assume, that's going to be a homeomorphism, and you're going to have a dynamical system like we did for the Cantor set example. In this case, too, you can do something like that, but you need to deal with this point. In this case, you still can do something, but it's more complicated. We're going to discuss this case and this case too, probably, after the break. Any questions so far? So this is the best case. This is the second best case. This is the worst case. Of course, the Pinski is also just touching. It's touching here, for instance. Questions? Okay, let's take a 5-minute break, and then when we get back, we're gonna start talking about how to actually build that phi function. Okay, welcome back. So this open set condition, it's somewhat of a terse thing to work with a little bit. When a B-IFS does satisfy it, it's relatively easy to verify that it does. When it doesn't, it's not that straightforward. So here's an example. I think this is very instructive to try to do this. I have x equals r, so the reals, first contraction is 2 over 3x, and the other one is this. And this, of course, looks like this. Okay, so this is W2, and the blue one is W1. And there's this intersection. Now, I gave this as an example of a B-IFS that doesn't satisfy the open set condition, but verifying that this does not, in fact, satisfy the open set condition is not that straightforward. So I would highly recommend this exercise. Because you're going to say, so for open set condition, you need one open set that satisfies these things. So in order for the open set condition to be not satisfied, you need to show that there is no open set that satisfies both of them. So it's not that straightforward. Okay, but still, if you're okay with using technology, it's actually rather straightforward to verify this, which is by way of this Moran-Hutchinson Dimension Formula that we're going to discuss and prove after the break, because it still involves certain phrases that we haven't discussed. Which says this, it's a preview for now. If I have a B-IFS W acting on X that satisfies this open set condition, and if you have this condition, that is to say, this Lipschitz constant is not only an inequality, but in fact, it's an equality for any 2 points. So this is what is called a similarity transformation, i.e., each Wi is a similitude, let's say. Then the upper similarity dimension of this B-IFS, which is the unique solution to a certain equation that we discussed before, is also equal to a bunch of other definitions, bunch of other dimensions in different senses. Then let me just write it. And this is going to be the case. So here, A sub W, of course, is the attractor. Dim sub H is the Hausdorff dimension. Okay, we're going to discuss this. Dim sub M with an underscore, it's called the lower Minkowski dimension, or it's a lower box dimension, or in Barnsley's terminology, it's the lower fractal dimension. And this is the upper Minkowski dimension. In general, these numbers are different. And this is the upper similarity dimension. So all of these turn out to be this number, T, such that this equation holds. In general, it turns out that computing these numbers for arbitrary sets is very complicated. Certainly, they are a lot more complicated compared to solving this equation, even approximately. So this is sort of like a very powerful thing. Let me also say that whenever this set, this attractor, is a nice set, each of these notions of dimension give you the obvious number. Okay? Now, in this case, what is the attractor to this B-IFS? Well, the attractor should satisfy this equation. And in fact, it's the unique compact subset that satisfies it. Well, if you were to choose A to be the interval itself, it certainly satisfies it. By the uniqueness, the attractor is the interval. Now, this is a nice space, nice set, which means that all of these numbers in that particular case are equal to 1. I still haven't defined these things, but I'm saying that whatever their definition, if you feed to them a nice set like an interval, it should give you back the obvious answer. So what is the upper similarity dimension of this? Well, so both of these are similarities, are similitudes. And Lipschitz constants for both of them is 2/3. So 2/3 to the power d, I have two of them, equals 1. Okay? That means that 2/3 to the d equals 1/2. So if you solve for d, that gives you log 2 over log 3/2. This is a number that is strictly greater than 1. Okay? Which means that these numbers, these dimensions, don't match with this dimension. Which means that by this formula, one of the hypotheses must be broken, and everything except this is broken, as you see. So by using the dimension formula, you can answer this exercise. But if you didn't know this formula, you would need to verify, or given any open set, if it satisfies one of the conditions, it doesn't satisfy the other condition, and so on. And it's a very nice exercise. Any questions about this so far? Yeah, I like describing theorems at least vaguely before stating them, because things are going to get ugly, as you can imagine. But anyway, so this is what's to come after the break. After the break, we're going to spend some more time on dynamics. I'm going to define certain things like topological mixing and stuff like that. We're going to look at how to deal with B-IFSs that doesn't satisfy the open set condition. There's a bunch of other things as well. After that, we're going to switch over to dimension theory, where we're going to spend some time discussing the definitions of these numbers. We're going to compare them. We're going to start using them. And then ultimately, we're going to prove either this or slightly a version of this that is slightly more general. OK, so now what we're trying to do is to build this phi function. So this phi function is often called the coding, because you have, on the one hand, a set that is sort of you don't know much about. It's the attractor. On the other hand, you have a shift space. A shift space you should imagine as sort of a set that you understand very well. If you've taken linear algebra, an attractor is sort of like an abstract vector space, and a shift space is like Rn, or it's like a Euclidean space, where everything is like a matrix and a vector and so on. Construction. Of the coding map phi from the shift space to the attractor. Now, first I'm going to introduce a certain gadget that is called a cocycle. Now, a cocycle, well, let me first say that remember when we first started discussing iterative function systems, I mentioned that there are 5 different ways of approaching iterative function systems. We used the monoid approach, we used the Hutchinson operator approach. The third approach was the cocycle approach, and now we're discussing that. Before defining this cocycle that we're going to use in this situation, I want to give some examples. Cocycles. Because in a sense, a cocycle is sort of like an abstraction of the notion of the chain rule in single variable calculus. So, example. And this is called the derivative cocycle. I'm going to take a differentiable function f on the reals. So it's a single variable function. Now I want to apply the chain rule to iterates of f. So let me just denote by d of n comma x the first derivative of the nth iterate of my dynamical system evaluated at the point x. Okay. The point is that by the chain rule, I can sort of like open this up and rewrite this expression using derivatives of f instead of its nth iterate. So let's do this. Okay. What happens if I look at this? So the derivative cocycle at time n plus m at x. Okay, so let's open this up. Sorry. Yeah, sometimes I'm just holding the chalk at the right height so that you have the resonance. But, okay, so what is this? This is the nth iterate function composed with the mth iterate, then I need to differentiate this. Well, how do you differentiate this? The derivative of the outer one evaluated at whatever this point gives, and then times the derivative of the inner one. So this is the derivative of the nth iterate of f evaluated at f to the m of x times the derivative of the mth iterate evaluated at x. Any questions about this? This is nothing sophisticated, single variable calculus. Maybe it is not familiar to you to sort of differentiate something like this, but I'm just differentiating chain rule. So this is d of m comma x. On the other hand, this is d of n comma f to the m of x. So I have this, what people would call cocycle relation, or cocycle identity. Any questions about this? Here's another example. I'm not going to do this. I'm going to give it as an exercise. It's very useful. Let's call this the tally cocycle. I have some function acting on some set x. And let's say that you have an observable. That is to say, you have a function phi taking points in x and giving real values. This is sort of like a measurement that you're sort of conducting. And so the tally cocycle is going to be this. Let's write it like this. So what does this mean? That's the measurement you're making. You start at an initial condition, and you're going to keep track of it up to time n. What you do is this. You look at what the value of your measurement is at x, and then what happens tomorrow at f of x, and then what happens 2 days later, and so on, all the way up to time n. And then you tally everything. The claim is that this too satisfies the cocycle identity. Now with addition, of course, instead of multiplication. Okay? Any questions about this? So at least from a formal point of view, this differentiation business is pretty much the same thing as tallying. Now, in our case too, it's going to turn out that we have a cocycle that helps us do things. Okay? And let me also say that when it comes to modern day dynamical systems, at least the pure version of it, I would say 95% of all problems have to do with understanding some sort of cocycle. Maybe it's more complicated than these, but still. So for our purposes, I think I'm running out of time. Let me just define it, and then we're going to discuss it later. So the cocycle that we're going to use is going to be defined like so. In those cases, I just had numbers. Now I'm going to have functions. This is equal to this. Now, we're going to see when we come back, and with this I'm going to finish. It satisfies this equality. Compose with sigma to the n of omega at m. So it's almost like this. The ordering is somewhat different. The operation is different, but it's a cocycle. We're going to do this after we come back from the break. Okay. Thank you. Have a nice break. I'll see you later.